Hello, my name is Abraham George, and today I want to talk about my research into using Python to help with the analysis of chondrites. Before I begin, let me briefly go over what chondrites are. Chondrites are a type of meteorite that is characterized by small mineral grains called chondrules, which are surrounded by a fine-grained matrix material which cements the chondrules together. A cross-sectional image of one of these chondrules can be seen in Figure 1. The reason we're interested in studying this type of meteorite is because they are some of the oldest materials in our solar system, at over 4.5 billion years old. This makes them extraordinarily helpful for trying to understand the conditions that occurred during the formation of our solar system. Now that we understand what chondrites are, the next question is why create a custom software in order to analyze them, especially considering that the electron microscopes we use often have built-in analytic software? Well, there are two main reasons. First, it allows us to design tools specifically for analyzing chondrites, rather than using the electron microscope software, which is designed for a more broad set of applications. Secondly, since we're coding this program in the open source language Python, we can easily go back in and edit the software to adjust for any future needs we may have. Okay, so how do we get this data that we're analyzing? So we get the data using electron microscope spectroscopy. Electron microscope spectroscopy is a type of spectroscopy that involves shooting a beam of electrons into the material. These electrons fly into the atoms of the material and collide with electrons in the inner shell. This creates gaps inside the electron's lowest energy orbitals. These gaps are then filled by higher energy electrons falling from outer orbitals into these gaps in the inner orbitals. And whenever those electrons go from the high energy orbital into the low energy orbital, they emit a X-ray. And we can then look at the X-rays, specifically the energies of these X-rays, and use that to fingerprint the chemical composition of the material emitting them. So, there are two main types of electron spectroscopy. The first one we want to look at is TEM microscope spectroscopy. This is really high magnification spectroscopy. And here, discussing these, we can really start getting into some of the basic analytic tools that we've developed. So, for example, you can see in Figure 3 two images. On the left, this is a sample that we've looked at that data come out of the electron microscope spectrometry, and then highlighted in yellow all of the places with iron contact. And the brighter the yellow, the higher the iron content there. On the right, a similar image, only this time it's a heat map between iron content and magnesium content. Now, these are only two examples of a qualitative analysis that we can do with this program, but the possibilities are endless. We can do these kind of maps with any element. We can adjust it depending on certain cutoff values, different weights depending on the relative abundance of the elements, and of course, because all of this data is in digital form, we can also do qualitative data analysis using statistics, finding trends and correlations, etc. So the second major type of electron microscopy is SEM. Now, for our purposes here, the main difference between SEM and TEM is SEM is at a larger scale. So whenever we look at these images, we get usually a picture of a whole cross-section or a large piece of the cross-section rather than a zoomed in one little bit of it like we get for the TEM. So whenever we're looking at this larger scale, a new problem arises. We want to identify where the chondrules are in this chondrite. That's because oftentimes whenever we're looking at this data, we want to be able to do separate chemical analysis on the chondrites versus the matrix. So what do? Well, we need to figure out where those chondrules are. The program does this by looking at the chemical signatures of the points, and then determining whether that point should be in a chondrule or matrix based on the composition of a variety of elements, including iron, magnesium, sodium, and nickel. So once we've done this analysis, we can then highlight these regions. In this case, you can see in figure 4, these regions are highlighted in yellow. And then we can proceed to do chemical analysis on here, comparing the concentrations of certain elements inside and outside of the chondrules, for example. So where do we want to use this code? So our major future goal at this point for this code is to use it in research for collision impacts in chondrites. Basically, whenever you have the rapid heating and cooling associated with collisions, how does that affect the chemical composition of these chondrites? And we're hoping to pursue that further this semester. So after looking at this poster, one question that might come to mind is, what are these techniques replacing? What did we do before using this code? So I think a great example of this is in the case of finding chondrules. So how did this code actually help? Well, in the case of chondrules, before we had a program to look for these chondrules, we would have to go through by hand and find them. Usually this meant going into basically paint and just coloring in the chondrules on this image. Now the program does it. That's not 100% yet, but it does a lot of the legwork for us. We can then go back in and touch up a few places, but it saves us hours of time for coloring in one of these images. That's all. Thank you so much for listening to this. I hope you enjoy the rest of the showcase. Goodbye.